Alright, welcome to the LRC Response. You guys have a lot of stamina for making it this far if you're doing it all at one kill. Really hope you're not doing this on the Friday that it's due. I understand. I was there one time as an undergrad. I also procrastinated to the last minute, and it suffered me greatly. Hopefully you're not doing that. Please, I beg you. But I mean, if you're at this point, oh well, I'll shut up and get going. Alright, so CSV will give you 3 columns: time, input, output. This will be your square wave. This will be your LRC response. This is a second order system, so you should see ringing, otherwise known as oscillation. Here is your full system. I only care about one of the oscillations, so it looks like this was my third. I think this is your third wave. Once again, does not matter. Pick whatever one makes you the happiest. Here is something interesting. So this will harken back more towards Lab 4. If you remember that, we had damped frequency analysis, right? If you'll actually remember, you don't need to shift your time. It's actually unneeded, because if you remember your equations that you use, if you try doing a shifting here, so this will be Tn plus 1 minus T offset minus the quantity T1 minus the T offset, the offset times cancel. So you don't necessarily have to do that. What you do have to do, however, that whole analysis for the damped oscillation is only valid when the oscillation oscillates about 0, or the x-axis. So what you're going to have to do is, here's my steady state value, so 1. In this case, you'll have noise, but you're going to create a column where you have to shift the output. So in this case, I just subtracted by 1. Again, if you're one of those unlucky souls that had like a peak to peak of 1.25 and an offset that wasn't half or whatever, sorry, I suck. I should have caught that. I didn't. You can email me complaints, or just, I don't know, silently mauled. Whatever works for you, honestly. So all I did here was I chose the rising edge. You could do the falling edge. Technically, if you do the falling edge, you don't have to do that offset. But we're no cowards here. We're going to do the rising edge, and we can see here I'm going to pick the data points that I could see the best, specifically the peaks that are well defined. This is where it gets kind of complicated. One could argue, well, technically you have a 4th peak. Yeah, maybe. The noise is too much, though, that it's kind of hard to make a good decision on what truly is the amplitude. This one I can clearly have 3 peaks. I think everyone will mainly have 3 peaks. You could do 2 peaks, that's fine if you don't feel confident with this third one, if it looks kind of weird. I saw some people's data where I'm just like, I don't know about that one. 1 and 2, though, those are definitely good. So you need to find the values of those peaks. Here is a nice little trick that I found. If you want to figure out this specific data point, double click till you're right on that data point, and then you're going to right click, add data label, do a call out, and look at that. Look at that. That's pretty cool. It freezes up sometimes for reasons I don't know why, but here the first one is your time, and that is your voltage response. So I think that's pretty cool. You should draw arrows. You should tell me which data points you are using for your analysis. By the way, here, since I'm only analyzing 3 peaks, my number of peaks is 3. The number of cycles is the number of peaks minus 1, right? So in this case, I just have 2. So I have these 2 values. I have the voltages and the times at which they occur. Also, in case you need to ever look at what I'm saying. Spent all this time practicing and loading these up, and then I just never address them. So good job on me. Anyways, number of cycles, T1 V1, T3 V3. This will be T1 and Tn plus 1, right? If you guys remember that. So here are the relevant equations that you'll end up using. I believe they are correct. I'm hoping they are correct. Here's your ringing frequency, by the way. Here is your delta, your logarithmic decrement, I think is what it's called. And then here's your zeta. So this is your damping factor, damping ratio, just damping. And then here is your natural frequency. To find the natural frequency theoretically for an LRC circuit, it is given by this equation. Once again, you're going to have to find the uncertainty using RSS. Sorry, but also not sorry. Here is your value. Here is your lower and upper values. Something important is to remember here is the significant figures. So the farthest one out was 470 millihenries plus or minus 5%. So that's actually pretty huge. Then you have resistor value of 470 ohms. So make sure your units are correct, or your sig figs. I think that might actually be incorrect. So egg on my face. I'll fix it later. Honestly, probably not. But yours better be really good, because no one's grading me on paper, just in their hearts and minds, which actually might hurt more. Anyways, here is your experimental value. Once you do this analysis, you theoretically could find the standard deviation of your experimental value doing a lot of error propagation. You guys are already doing so much. I'm gonna do you a freebie. You don't have to find the standard deviation of your experimental values. I guess if you found the second your falling side, you could have some standard deviation. You don't have to, but you can see here I plotted the lower and the higher, and hey, look at that, falls right in there. In fact, it's so good it looks like our error is not that, or that our percent error is not too high. So that's pretty cool. It also asks you to find your peak overshoot. So what you have to do is have a normalized voltage. So you'll make another column where you'll have your output divided by whatever your peak, or your what it should level out to. So in this case, right here for me it was 1. Someone might have 1.5 or 1.25, whatever it levels out to up here. You have to divide it, because basically we're doing a percentage here. I got lucky, and this is why I wanted people to do a peak-to-peak of 1 and offset it at 0.5, because it just oscillates at 1, which, you know, easier work. But anyways, you can do a little bit of cheat seeing here. Just pick this peak voltage, which is this value, 1.49, and that is your percent overshoot. You can go into this column and basically also find that value. But yeah, so there is a question, right, of what happens if you increase or if you double your damping. Well, let's look at this chart. Here I basically, just for my data's sake, I went through, assumed that the ringing frequency was the same, and you can see a difference, right, when I choose a different damping, when I multiply it by 2. But we can look at this chart. You can go to this website, which by the way you should, especially in your report, and show this graph, right? So here's 0, so it's just a pure sine wave. 0.1, so you can see it starts to damp. Sorry for the low quality. So we can see if we double it, if we quadruple it, our overshoot not only decreases, but look how fast it levels off to what it should be, right? You can also see when it's critically damped, you actually have to wait longer for it to reach the value of which you want, right? And then if you over damp it, so in this case twice, you not only get a longer decay, but now you have to wait even longer for it to give you the correct value, right? So this is why we like to under damp our systems using an LRC circuit. You just have different kinds of error, but it's errors that you can maintain. I think that is everything that you need to do for the LRC circuit. I think that's everything you need to do for the response. If you have any questions, you know how to reach me. Feel free to reach me, and I will try to respond to you as fast as possible. If you're watching this before Thanksgiving, happy Thanksgiving. Hope everything goes well. If you are watching this after Thanksgiving, hope everything went well. And I really, really, really hope this is not being watched on the Friday of which it is due. So anyways, good luck, guys. I'll see you later.